Lab number 2, observing osmosis in living cells. Purpose, explore comparative effects that different solutions, sodium chloride, water, and sucrose have on a red onion cell. If salt water reached the roots of a plant, what would happen? The salt water would become sodium and chloride particles, which are toxic to the plant. Dehydration can occur, and if the environment becomes isotonic with salt water concentration, the cell will not be able to perform osmosis and will die. Water potential is the tendency of water to move from one region to another. Water diffuses from a high concentration to a low concentration. Water will move out of the cell because the cell has a higher water potential than its environment. Hypothesis: the sodium chloride will plasmolyze the cell. Sucrose will make the cell flaccid, and water will make the cell turgid. Materials that were used. Procedure: a wet mount of red onion skin was observed under a microscope on low and medium/high power, and observations were recorded. 2 to 3 drops of sodium chloride were dropped on one edge of the cover slip, and it was drawn out from the other side using a paper towel. It was observed under a microscope, and a single skull was sketched. The cover side was removed, and the onion cell was flooded with distilled water. It was observed under a microscope with high power. Observations recorded. Step 2 was repeated with sucrose. Observations: wet mount with low power, wet mount with high power. Sodium chloride, flooded with distilled water. Sucrose.
Turgor pressure is controlled by the amount of water diffused out of the cell or into the cell. The central vacuole of the tonoplast and aquaporins of the plant cell help maintain turgor pressure. As seen in our observations, as water is added into the onion cells, the central vacuoles, the pink blobs, swell up due to osmosis. They were different sizes depending on how much water was let in or out of each cell and its central vacuole. The water content is what determines the amount of turgor pressure and causes the cell to be flaccid or turgid. The tonoplast, which is the membrane of the vacuole, helps the cell maintain osmotic balance by allowing water to enter and leave the vacuole through its channels. Like the tonoplast, aquaporins are specialized channels for water of the plasma membrane that speed up osmosis. A contractile vacuole collects and expels the excess water that accumulates in the cell. Since a freshwater single-celled organism has a semi-permeable membrane and is in hypotonic solution, water diffuses into the cell because it has a lower water concentration than fresh water. Since water enters the cell by osmosis and causes it to swell, it needs a contractile vacuole for osmoregulation to prevent it from experiencing cytolysis. Since ocean water is a hypotonic solution, it has a higher osmotic concentration and a lower water concentration than a single-celled organism living in salt water. For these reasons, osmosis will occur naturally. A contractile vacuole collects the excess water that accumulates in the cell through osmosis and then expels the water out of the cell. However, since water is already naturally leaving the cell, having an additional method to drive water out is unnecessary. If a contractile vacuole did exist in a saltwater single-celled organism, it would rarely be used because the cell would want to maintain osmoregulation. Expelling too much water from the cell would disrupt the water concentrations of the cell and the salt water, which would cause rate of osmosis to become unsteady. The rate of osmosis needs to be consistent in order to have osmotic balance. Osmotic imbalance would cause plasmolysis, and the cell would shrivel up too much and die due to cellular dehydration. The principle of osmosis is that the solvent diffuses from the solute side of high concentration into the solute side of lower concentration. Food preservation is used to prevent bacteria, fungi, and other microorganism growth that causes food to spoil. The presence of water is what allows microbes to grow. Food is stored in a solution containing a concentrated amount of salt solutes for preservation. The addition of salt solutes increases osmotic concentration and decreases water concentration in food cells. The change in concentration speeds up the rate of osmosis, which dehydrates the food cells. This is because water is being diffused out of the membranes more quickly. Microbes need water to transport nutrients in their cells, however, the dehydration of the food cells will not allow the microbes to thrive, therefore it will slow down the process of food spoilage. Water potential is the tendency for water to move, where it always moves from a higher water potential to a lower water potential. Any plant with a leaf or a small shoot like twigs, branches, herbs, and fruit can have its water potential measured using a pressure chamber. Part of the leaf or shoot is cut and partially sealed in a device and air pressure is applied. Originally, the water column of the xylem is under tension, but once it's cut, water diffuses into the plant cells exposed to the cut. The amount of pressure it takes for the water to emerge from the cut area is what declares the water potential. Another way to measure water potential is to use a synchrometer. A synchrometer measures the water vapor pressure of a solution or a plant tissue, the root, stem, or leaf, such as a tree or a flower. The tissue is put in a small chamber and touches the droplet of known solute concentration. In the chamber, there is a temperature sensor. The diffusion of water from the droplet to the tissue, or vice versa, will change the temperature of the droplet, making it cooler or hotter. Water potential can be measured once the change in temperature is calculated.
Created using Powtoon.